Mass tells matter how to fall, but mass is only half the story. Matter carries a second property, one that can push as easily as it pulls: electric charge. The force between two charges follows a law that looks almost exactly like gravity, an inverse square reaching across empty space. And hidden inside both laws is the same quiet symmetry. Every force comes in a pair, equal in size and opposite in direction. By the end, we'll prove that gravity and electricity both obey Newton's third law for one and the same reason. Start with charge itself. Unlike mass, which is always positive, charge comes in two kinds, positive and negative. The rule is simple and symmetric, like charges repel. Two positives push apart, two negatives push apart. Opposite charges attract. A positive and a negative pull together. We measure charge in a unit called the Coulomb. So matter has two independent handles on the world: its mass, which only ever attracts through gravity, and its charge, which can both attract and repel. Charge doesn't come in any amount you like. The smallest free charge in nature is the charge on a single electron or proton. We call it E, and it equals 1.602 times 10 to the minus 19th coulombs. Every ordinary object carries charge in whole number multiples of this amount, so charge is quantized. Any charge Q equals some whole number n times E. The electron carries exactly 1 unit of negative charge, so Q sub E equals minus E. The proton carries 1 unit of positive charge, so Q sub P equals plus E. And charge is conserved. In an isolated system, the total charge stays fixed, and in a closed system, charge can only be transferred from one object to another, never created or destroyed. Now the fourth law itself. Take 2-point charges Q1 and Q2, separated by a distance r12 in a vacuum. The electric force on object 2 from their interaction is given by Coulomb's law. It equals K sub E times Q1 Q2, divided by r12 squared, all pointing along the unit vector r hat 1, 2, the direction from object 1 to object 2. That unit vector is just the separation vector divided by its own length. The constant K sub E equals 8.9875 times 10 to the 9th Newton meter squared per Coulomb squared. Notice there is no minus sign out front. The sign lives entirely in the product Q1, Q2. Same sign charges give a positive product, so the force points away, repulsion. Opposite charges give a negative product, so the force points back, attraction. This inverse square law was derived empirically by Charles Augustin de Coulomb in the late 1700s. Picture it in two cases. On the left, two positive charges. The force on each points directly away from the other. Along the line joining them, they fly apart. On the right, a positive charge and a negative charge. Now the forces point toward each other, along that same line. They're drawn together. In both pictures, the two forces lie on the line connecting the charges, and though we haven't shown it yet, they are always equal in strength and opposite in direction. That last fact is Newton's third law, and it's exactly what we'll prove next. Here is the payoff, example 8.1. The claim, both Coulomb's law and Newton's universal law of gravitation satisfy Newton's third law. That is, the force object 1 feels is always equal and opposite to the force object 2 feels. Let's prove it for gravity first, then watch electricity follow for free. Recall the gravitational force on object 2 from the interaction of the two masses. It equals minus g times m1 m2 divided by r12 squared along the unit vector r hat 1, 2, which points from 1 to 2. That leading minus sign is what makes gravity attractive. The force on 2 points back toward 1. Now we want the force on object 1 instead. We get it by interchanging the labels 1 and 2 everywhere, so the force on 1 equals minus g times m2 and 1 divided by r21 squared along r hat 2, 1. Look carefully at what actually changed. The masses only swapped order, and M2, M1 is the same product as M1, M2. The distance is the same separation, so R21 equals R12, and the square distance is unchanged. The one and only quantity that genuinely flips is the unit vector. R hat 21, the direction from 2 to 1, is exactly the opposite of R hat 12, the direction from 1 to 2. So R hat 21 equals minus R hat 12. Substitute that in. The minus sign from the unit vector combines with the leading minus sign, the two negatives cancel, and the force on 1 becomes plus g times M1 M2 divided by R12 squared along R hat 12. But that expression is precisely the negative of the force on 2. So the force on 1 equals minus the force on 2. The two gravitational forces are equal in magnitude and opposite in direction, exactly what Newton's third law demands. And Coulomb's law? The argument is identical. Swap the labels, and again the only thing that changes sign is the unit vector. The charges Q1, Q2 commute just like the masses, and the distance is unchanged. So the electric force on 1 equals minus the electric force on 2 as well. One structural feature that the force lies along the line joining the objects and the reverses when you swap them guarantees the third law for both of nature's inverse square forces. Step back and see what we've built. Matter carries charge as well as mass. Charge is quantized in units of the fundamental charge E, and it is conserved. Coulomb's law gives the electric force between charges, an inverse square along the line joining them, repulsive for like charges and attractive for opposite ones. And beneath both electricity and gravity sits the same symmetry. Swap the two objects, only the direction flips, and every force is met by an equal and opposite partner. Newton's third law built into the very form of the law. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.